Hey everybody, welcome back to another chemistry video. Today we're going to be discussing the material that has been covered in class before this Unit 4 test. So let's dive into it. So here we have ion formation and periodic trends. This is just a quick review, but we know that metals form cations, positive charges where electrons are lost, and nonmetals form anions, which are negative charges where electrons are gained. And just a couple examples, gallium loses electrons, aluminum also loses electrons to form aluminum plus 3, and oxygen gains electrons to form oxygen 2 minus. And for periodic trends, we just need to remember that the metals are on the left side of the periodic table, and the nonmetals are on the right side of the periodic table, and the transition metals are in between. So now we need to know the difference between ionic and covalent bonding. This is important. I know this unit has been all about ionic bonding, but covalent bonding did show up on the previous quiz, so I just want to address that and make sure everybody knows what covalent bonds are. So ionic bonding, we already know metals and nonmetals. Electrons are transferred. Covalent bonds are nonmetals plus nonmetals, where electrons are shared. And just a couple examples, barium plus oxygen is ionic, lithium plus oxygen is ionic, but over here we have our covalent bonds. We can see that all of these are nonmetals. Carbon plus oxygen, sulfur plus oxygen, and phosphorus plus oxygen. So now we need to understand the properties of ionic compounds. We need to know what exactly an ionic compound looks like, what are its properties. So in the solid form, ionic compounds form crystalline structures. They have high melting points and boiling points. They are solid at room temperature. They can conduct electricity when melted or dissolved in water, and they can be brittle, not malleable. So this you'll just have to memorize, and I like to take NaCl as your example. NaCl is table salt. It forms a crystalline structure in its solid form because all of its ions are confined to a certain structure in the solid form. It's pretty straightforward. Salt, NaCl, will have a high melting and boiling point. It's solid at room temperature. Obviously, if it's on your table, it's solid. And if it is dissolved in water, we all have dissolved salt in water before, that's when it can conduct electricity because the ions are no longer confined to a solid structure. Electricity can be transferred through these ions, and they can be brittle but not malleable. So this all happens because ionic compounds have strong attraction between positive and negative ions. So yeah, this is just what you'll have to remember about ionic compounds. So now we're moving on to acids. And acids release hydrogen ions in water. And you just need to know how to name the acids, and there are three major naming patterns. So if you have an acid without oxygen in the name, it's going to be hydro plus root plus ic. So for example, we have HCl, hydrochloric acid. We have HBr, hydrobromic acid. As you can see, there's no oxygen in these formulas. So if we have an acid with oxygen in the formula, all the ate will end in ic, and the ite will end in ous. So for example, we have a hydrogen in the front, NO3, nitric acid. We have hydrogen in the front once again, sulfuric acid, and anything that ends with ITE will end with OUS, as I said. HNO2, nitrous acid, H2SO3, sulfurous acid. So also just remember that anything that has a hydrogen involved in the formula will be an acid. And these are my notes straight from class. This was on Dr. Sankar's board. So please take a look at it, screenshot it, make sure you know what's going on over here. It's basically everything I just said, slightly longer, slightly more detailed. So now we're moving on to bases. A base can be defined as a substance that yields hydroxide ions, OH minus 1. So most bases are metal hydroxides, NaOH, sodium hydroxide, CaOH2, calcium hydroxide, and I took this picture right from the slides, but bases are pretty straightforward. They usually just contain a metal and the hydroxide ion, and they are the names using the rules for ionic compounds. Um, yeah, that's pretty much it for bases. This one's pretty straightforward, pretty easy. So, yeah, let's move on to hydrates. And hydrates are ionic compounds that contain water molecules trapped in their structure. So, imagine we have that table salt situation again as an example. Imagine there are water molecules stuck inside those little crystalline structures of table salt. As you can see in the picture down here, I'm pretty sure that's what it's trying to depict. That there's like little water molecules stuck in these little crystals. But yeah, hydrates just have water molecules trapped inside. So when you name hydrates, it's going to be the ionic compound plus the Greek prefix and then hydrate. So depending on how many water molecules are involved, that's going to be your Greek prefix. Mono is 1, di is 2, tri is 3, tetra is 4, and so on and so forth. So as we can see again, in this picture I pulled right out of the slides, we have some naming situations. Barium chloride with 2 H2Os. So it's going to be barium chloride dihydrate. And just remember that this dot in the middle is not a multiplication symbol, it's going to be with. So it's barium chloride with dihydrate. So that's pretty much it. We have just a couple examples over here. Yeah, bases and hydrates are going to be pretty straightforward. And again, bases are just ionic compounds which have hydroxide ions. Hydrates are ionic compounds which have water molecules trapped inside. So, yeah. Now we have transition metals in Roman numerals. And let's first understand why Roman numerals are needed. So most of these transition metals can form more than one possible charge. They have multiple oxidation states. So just know that multiple oxidation states just means that they can form more than one possible charge. You will probably see either of these phrasing on the test. And because of this, their ionic compounds must specify which charge the metal has. So we indicate the charge using a Roman numeral in parentheses after the metal's name. So, for example, we have iron, copper, chromium, cobalt, tin, and lead. These are going to be the most common transition metals that you see with ionic compounds. And these are the most common oxidation states that each of these transition metals have. Iron 2 or iron 3, copper 1, copper 2, chromium 2, chromium 3, and so on and so forth. And these are, this is just how you would write them, as we always do. 2 plus 3, 2 plus 3, and these transition metals, they are metals, so they're always going to form cations. So again, for example, we have iron chloride, iron and 2 chlorine. Chlorine usually forms a -1 charge, and compound has 2 chlorine, so a total of 2 minus. So iron must have a charge of +2. So again, using the crisscross method, we know that iron's going to have a charge of +2, chlorine's going to have a charge of -1. So we're going to need to have 2 chlorines, 2 chlorine atoms to match the amount of electrons that iron is losing. I hope I made that clear, but pretty straightforward, just like bases and hydrates. Everything is going to be pretty simple in this unit, so I'm hoping I'm making sense. And finally, we're going to be determining ionic character. So essentially, the larger the electron negativity difference between two elements, the more ionic the bond is. So most ionic bonds are going to be metal plus nonmetal, and especially when they're far apart on the periodic table. So we know that the electron negativity increases down a period and decreases down a group. So essentially, the farther apart the metal and the nonmetal are on the periodic table, the more electron negative it's going to be. So the most ionic ones are going to be metal plus nonmetal far apart on the periodic table. For example, cesium and fluorine, NaCl, salt once again. And least ionic are going to be the bonds with elements that are closer together. So even if it's a metal and a nonmetal, a small electron negative difference is going to mean it's less ionic. For example, HgCl2 has visible covalent character. So it is an ionic compound, but since it's less ionic, it's going to have more of a covalent bond character, We did not discuss the properties of covalent bonds because this is not what this unit is about, but we did discuss the properties of ionic bonds. And since this is one of the least ionic compounds you can have, it's going to have some covalent character. I hope I made sense. And again, just a refresher, electron negativity is a measure of how strong an atom attracts electrons when it is in a chemical bond. And like I just said, electron negativity increases down a group and decreases, or increases down a period, and decreases down a group. And fluorine is the most electron negative element. Francium is the least electron negative element. So, yeah, thank you guys so much. I wish you the best of luck on the upcoming test, and I will leave a Google link or a link to a Google form in my YouTube bio. Um, Please fill it out if you want to schedule a one-on-one session. If you have any remaining questions or you want to study, you know, you want to study together or anything. So, yeah, this is gonna be like a tutoring type of thing, just an extension for my YouTube videos. So again, thank you guys so much. I'll see you in the next video. Good luck on the test.